Welcome back. Remember that we introduced the Carnot-Caratheodory distance, aka the subRiemannian distance on Heisenberg group, before introducing its group structure. In this lecture, we want to show that the distance is in fact left invariant, that it respects the group structure of Heisenberg group. A quick recall how this distance was defined in the first place. We called an absolutely continuous curve in the manifold R3 a horizontal curve if its velocity, lied in the span of the so-called horizontal vector fields x and y, almost everywhere. For such curves, we define the distance, assuming it's parameterized without loss of generality over 0, 1, by integrating this length. In other words, we have declared x and y to be unit length and perpendicular. Then the distance between given points is the infimum of such length over all horizontal curves that join P and Q. We went through a lot of pain, in fact, to show that such a curve exists, at least one such curve exists, and we gave some estimates over the distance to the origin. Namely, for instance, we saw that the distance to the origin of a point zt, where z is the shorthand for xy, is comparable to absolute value z plus absolute t to 1/2. And I'm not sure even if we showed that any arbitrary pair of points can be connected. Maybe we did. But anyway, it was easier to show that any point is connected by a horizontal curve to the origin. And generally, the analysis with one of the points being the origin is simpler, at least for technical calculations. So once we know the distance is left invariant, we can then easily transfer any other pair of points so that one of the ends happens to be the origin. So the idea is represented in this picture here. Suppose you have points P and Q and you want to find some horizontal curve that connects them. What you do here is you come back and look at the point P inverse times Q, now that we have a multiplication in the group. It happens to be some point, and let's say we bring our knowledge of one point being 0 to know that there is some horizontal curve connecting 0, 0 to that point. Now my claim is that if you left translate that curve, it remains a horizontal curve and it connects P to Q. So let's go through these claims. So maybe let's call them lemmas. Lemma 1, if gamma parameterized, say from 0, 1 into R3 or H1 is horizontal, then left translation by a point G composed with gamma given by, so to be specific, LG composed with gamma acting on T will be multiplied by G, the value gamma T. The claim is that this curve is horizontal and its length, so length of LG composed with gamma, is exactly equal to the length of gamma itself. Well, we know that group multiplication, so all of gamma t, image of gamma t, is within a compact set, So LG is Lipschitz on this set. If you look at the formula for the multiplication, it's a bunch of polynomial operations in each variable, involving x's, 2x's, minus 2y's, and stuff like that. And if you restrict yourself to a bounded region in R3, these are Lipschitz operations. So if since gamma, let's say, because it's horizontal, it's absolutely continuous. So since gamma is absolutely continuous, LG composed with gamma is also absolutely continuous. So remember, to prove that a curve is horizontal, we have to prove first that it is absolutely continuous. Then almost everywhere its derivative is horizontal. Now let T be such that gamma prime of T exists and lies in span of x at gamma t and y at gamma t. So from differential geometry, we know the following. LG composed with gamma as a curve, its derivative at t will be, so its composition of a smooth operator, which is LG, with a curve, it will be the derivative of LG applied, it's a linear map, to gamma prime at t at such t. But LG, because it's left invariant, so by definition of left invariance, this means that since dLG preserves span. Okay, let's do this. So sends, so the LG sends horizontal vectors to horizontal vectors. This is from previous lecture, but that we saw that x and y are invariant under translations, left translations. That means because gamma prime lies in the span of x and y at gamma t, therefore, so I should say horizontal vectors at gamma t to horizontal vectors at g times gamma t, which happens to be LG applied to gamma t. So since this is the case, we see that derivative of LG gamma prime t lies in the horizontal subspace, that means the span of x and y vectors at the image of the curve. So since such t, or almost every t, at almost every t we have these two conditions, therefore LG composed with gamma is horizontal as well. Now for the second part, it's basically the same. Actually, we could probably be smarter and combine the two proofs into one. If at some t from above, gamma prime of t is a x of gamma t plus b y of gamma t, then Lg composed with gamma prime at t will be a x at L composed with gamma of t plus b y at L composed gamma of t. And this will be simply because here it's not important that a and b are variables. This is happening after we take the derivative, and the reason here is because dlg applied to x at gamma t is equal to x at lg composed with gamma t. This is just definition of left invariance of the vector x, and similarly for y. For y. Okay, and if this is the case, then L of gamma, which will be integration of square root of a squared plus b squared, will be exactly the same as computing with length of Lg composed with gamma. So that will be end of the lemma. If you start with a horizontal curve, the left translation keeps it horizontal, and moreover the distance is exactly the same. So a corollary of that will be that given P and Q in the horizontal, in the Heisenberg group H1, distance, Carnot-Caratheodory distance of P from Q is exactly the same as the Carnot-Caratheodory distance of 0 from P inverse Q. And the proof will be, well, by definition, DCC is infimum of length of horizontal curves. So every horizontal curve, we can say for every horizontal curve gamma from 0 to P inverse Q, the curve LP of gamma is, by lemma, a horizontal curve from, well, the ends will be multiplied by p. P multiplied by 0 is p, and p multiplied by p inverse q will be q. So it will be from from p to q with the same length, with equal length to gamma. So therefore, the distance between P and Q is not longer. It's shorter, theoretically, but not longer than that by definition of infimum. But conversely, if gamma is, let's say tilde is a horizontal curve from P to Q, then the left translation by P inverse is a horizontal curve. Notice I never mentioned left translation, so to go back to the origin, I don't do right translation. It's always only left translation. So is a horizontal curve from, well, multiply P inverse into the beginnings and ends. So tilde from 0 to P inverse Q. So that means, so this implied that dCc of PQ is less than dCc of 0 P inverse Q. And this implies the opposite, so 0 and P inverse Q is no longer than dCc of PQ. So, claim follows. And from that actually left invariance follows, because you can translate to any other point and you will get the same. So let's technically, we haven't proved this, but it's easy. So the main corollary, which was the topic of this lecture, is that dCc is left invariant. Proof. Okay, so dCc, so first of all, this means that dCc of P and Q is equal to dCc of any R times P, R times Q for every triple of points in the Heisenberg group. Well, the proof will be PQ is dCc of, from the corollary, 0 and P inverse Q. So these are from previous corollary. And dCc, separately applying the same corollary, will be dCc of inverse of the first one, 0 to the distance of 0 to first one inverse the second one. That's what corollary says. But this is equal to, if you do the group multiplication, be careful that this is non-abelian, so P inverse R inverse R Q. But these R's cancel now, they are next to each other, so it becomes 0 and P inverse Q, ending the proof. We just proved this equality from the corollary. This left invariance, as I mentioned at the beginning, helps us a lot with understanding the distances. If we prove, for example, that to every point other than 0 there is a unique geodesic, or just a geodesic from 0, 0 to that point, then by left translation we can claim the same for arbitrary pairs of points, therefore proving that the Heisenberg group is a geodesic. In fact, it's not uniquely geodesic, but we can characterize exactly for which points it is not. And again, if we do the analysis with just the origin, we can always left translate to other locations as well. And one of the important corollaries is that dCc of P and Q, which we just showed that is precisely equal to 0 and P inverse Q. And this will be comparable to, because distances to 0 were comparable to Z plus T to 1/2, if P inverse Q is written as a Z and T. But from group operation, we can compute these in terms of just coordinates of P and Q. You just apply the group formula, the group multiplication formula. We will indeed see that we could use this very equivalence, by Lipschitz equivalence, as a definition of distances without going through this notion of horizontal curves, infimizing the length and stuff, and that is called the Carnot metric. The idea why it is equivalent to the dCc metric, the proof is basically here, but I will do a separate lecture on that. But here's a kind of motivation for it, because we can reduce everything to distance to 0, and previously we've seen that distance to 0 of such a point is comparable to this quantity. If you have any questions about the proofs or corollaries, please let me know, and see you in another video.